recording here. All right. So by request, as I was saying, we're going to go through assignment 2, hopefully to fill in some of those gaps. You were on the edge, dropping the course. Forget it. Forget it all. That's fair. Yeah, that's totally fair. But let's go through it, and then hopefully we can kind of sort some of these things out. So if you felt like assignment 2 was so easy, you don't have to be here today. This is just for anyone who thought it was hard, which is, I think, everyone. So, all right. So let's see here. Oh, and also you have an assignment that's due on Friday, but I've already had a little bit of a warning that it's kind of a busy week for you guys. So I think I'll bump it till Sunday. I can bump it till whenever, but I feel like Sunday night would be probably a good cutoff point. And so assignment, can't remember what assignment it is. Yeah, 2 quizzes tomorrow. Oh my gosh. Let's say assignment number 3. Just to clarify which one I mean, I'll say was due on Friday, but now due on Sunday, October 31st on Halloween. That's not cool. Monday. I can't make something due on Halloween. Are you insane? Monday, oh, and then it's not October anymore. November 1st at 11:59. Yeah, you gotta go trick-or-treating. Or at least hand out candies, right? You'll be busy. I guess you could do it before Halloween, but that's okay. I don't wanna be the one who ruins your Halloween. So assignment number 3, I think it's number 3, I'll have to check, but yeah, so I'll bump that to Monday, November 1st at midnight. Okay. So today we will go through assignment number 2 together. It's the 1.5 to 1.7 sections together. So the first one, 1.5.8, I should pull up the textbook so I can read the question. Sorry. I'm sure you're all too familiar with the questions themselves. Okay, so we're given that a random variable has the CDF. So remember, by definition, the cumulative distribution function gives the probability up to some point of being less than or up to some point. Okay, and so X has, I'm going to paraphrase the question a little bit. X has CDF f of X. It's going to be 0 if X is less than -1. It's going to be X plus 2 over 4 if X is greater than or equal to -1 or up to 1, but not including 1. And then it's going to be 1 if X is greater than or equal to 1. close that up in curly brackets, and we've got our CDF. So then you were supposed to write an R function, but I hope I said, did I say for that one? Let me check. Is that the one that I said use Desmos? There was one that I didn't realize had R code, and I didn't say use Desmos instead, but anytime it says use R code, you can use Desmos. Yeah, so this one, you can use Desmos to solve instead of R. Okay, so in Desmos, we're going to sketch this thing out. Okay, so I think it says sketch in Desmos. So I'll bring in that graph, you'll have had it, and then use your graph, use the graph to find part A is the probability that X is between 1/2 and -1/2, or other way around probably. I'll start there and then I'll bring in the graph here. So what do we have? Well, if X is less than -1, it's 0, right? And so, okay, up to -1, it behaves, it's just a flat line at 0. And then between -1 and 1, it's going to behave like X plus 2 over 4. Okay. And then after 1, it's just going to be at 1. Okay. So I'm going to focus on, oh, and here's I guess some other questions for later that I was working on, but I'll delete those for now. And so what I have is X plus 2 divided by 4. Pretty sure that's what it was. Yeah. So now, of course, we have this straight line. Okay. Gonna screenshot that, save, bring it in. I'm getting better at this, I think. Okay, so what we're told is that after -1, it's down here at 0. Right, and so here, and then after 1, it jumps up to 1. So it's really only this section where it applies, or sorry, going to 1. -1, oops, negative, come on, to 1. Huh? Okay, so we're going to try to use this to find the probability that X is between -1/2 and 1/2. Now, what does that look like in terms of the graph here? Well, if X is at 1/2, 1, 2, 3, 4, 5, okay. Make it nice and tricky here. And -1/2 here. Okay. What can we do? The output at this point at +1/2 versus the output here at -1/2. These are the CDFs, right? So this is the probability of being up to and including 1/2, right? And what's kind of tricky, as at least when you're beginning, is that the endpoints, whether they're inclusive or exclusive, typically doesn't really matter on a straight line. And so that can be hard, right? Because then we're approaching, even if it's not at 1/2, at X equals 1/2, we're still approaching that point, and so we can still talk about it. But so what we want is we want to find the probability of being up to and including 1/2, right? Same thing, and then we can lob off the probability of being up to and including -1/2. So we can rewrite this in terms of the CDF. And maybe what I'll do is I'll bump this down here. for now. And just kind of scoot this over here. Okay. So this probability, maybe I'll give myself, sorry, just a little bit more room. I can rewrite because I have the CDF, right? So typically we would probably want to use the distribution function, but because we have the CDF, we can use it to find probabilities. So the probability that x is between -1/2 and 1/2 is the same as f of x, f at 1/2 minus f at -1/2. Okay, so we leverage knowing the CDF to solve this problem. And so what we find, and what you probably found, was that if I can add lines, and I find that it's the easiest way to do it. Y equals -0.5. Oh, that's not what I wanted. Sorry. Am I doing this the way I wanted to? Yeah, because x is the point. Okay. So then x, sorry, is -0.5. Okay, so then I can hit that point and it'll show me what the intersection is. So then if I look at, sorry, I wanted to do y again, x equals 0.5, then I have these two endpoints, and I think it'll only let me look, oh, there we go. All right, and so here, I'll screenshot this. I'm gonna just crop it up here so we can really focus on the values that we're finding here. So the output when x is 1/2 is 0.625, and the output when x is -0.5 is 0.375. Okay. So 0.625 minus 0.375. 0.625 minus 0.375 is 0.25. So that's that probability. Now the next probability that we want, just rearrange here, is I want to find the probability that x equals 0. Oops. My pen has been doing weird stuff lately, so see how this goes. But so the probability that x equals 0. So one of the things here is that, okay, well, x equals 0 is in this interval, right? It's between -1 and 1. But the problem with finding individual probabilities on this continuous curve is that they don't exist, right? We need some sort of interval to find the probabilities. And so here, the probability that x equals 0 is 0 since there's no interval. Since there is no interval, right? You can think of it kind of as saying, okay, f of 0 minus f of 0, right? That's basically what you would want to do. So then 0 minus 0, or something minus something, is 0. Right? And so because there's no interval on this continuous scale of x plus 2 over 4, that's why it becomes 0. And that's just a rule for any probability. It gets tricky because later we'll see when in that transition, then we'll be able to find probabilities. So it's kind of weird, but okay. So for C, we want to find, oh yeah, so here's the one where it's kind of weird. X equals 1. Okay. Because x equals 1 is one of those transition points, then we have different values. So here up to 1, it behaves like x plus 2 over 4. And then at 1, it transitions to just being 1. So no, so that's exactly what I'm gonna do. Right, as we approach x equals 0, technically from the left and from the right, I guess, but usually from the right because x at 1 is 1. So we'll leverage that, but that's exactly what I'll be doing as well, or arguing. So here, right, I know that very, very, very close to 1, I know how it's going to behave, right? And so I can figure out what it is at 1 or around 1, right? Since this is a transition point, we can find the probability. We can find this probability. Okay. So how I think of it is exactly what we saw in the chat there. I think of it as f at x equals 1. And then what I do is minus the left endpoint. So the probability of being at 1 is the jump, it's the distance from the line here at x plus 2 over 4 up to 1, right? So that distance is actually going to be the probability of being at 1. So now how I'm going to do it, and it's kind of, you know, not great, but x approaches 1 from the left. Which is going to be what? It's going to be 1 minus x plus 2 over 4 is 1 plus 2 over 4. 1 minus 3 over 4 is 1 over 4. So I guess, yeah, technically we could, yeah, sure, we can do that. But I'll just write this out, 1 over 3 over 4, oops. Okay, so we can use the same logic, but what happens is we have, and let's extend this a little bit more as x goes to 1 from the right. How about that? Because then it's going to be easier to see how it behaves around 0. So then what we have is, okay, I'm going to bump this down. I know you probably don't have room, but you can squeeze it in somewhere. There. So here, or by the same method as C, the probability that x equals 0, we can think of as the CDF at x as x goes to 0 from the right, minus the CDF at as x goes to 0 from the left. Now on this line here, right, x equals 0 is right here in the middle. And so as I approach it from the left as well as from the right, I end up at the same value. right? And so what I get is this becomes 0 plus 2 over 4 minus 0 plus 2 over 4. And I didn't give myself enough room here. Fine, I'll bump this down. 2 more lines. Two over 4 minus 2 over 4 gets us to 0. Okay. But it's because it's not at a transition point, right? It's using that same CDF. Okay. Good. Here, I'll do that one. Okay. I think that's good for that one. I haven't seen any questions in the chat. So the last one we want to do is the probability that X is between 2 and 3. That's going to be the same deal, right? We're basically going to end up at 1 minus 1. So let's use the same logic here, except now we have 2 endpoints instead of just 1. And so now that's going to be f of 3 minus f of 2. But f of anything greater than 1 is all going to be 1, right? And so 1 minus 1 is 0. One minus 1 is 0. Okay, good. I think that's it for that question. Switch here. Okay, so the next one is the tricky one. It's a really tricky one. So this one hopefully wasn't so bad. As soon as you probably figured out that you could use Desmos to kind of figure out the outputs, then it's not terrible. 1.6.3, I think, is the next one. Flip to it here. So 1.6.3, we're going to cast a die, and we want to see the number of independent times until a 6 appears on the upside of the die. And so we cast the die. Until a 6 appears. So first thing we're going to do is we're asked to find the PMF. This is discrete, right? Because I can only cast the die 0 times doesn't really apply because then I can't get anything. 1 time, 2 times, 3 times, 4 times, 5 times, etc. And so find the PMF. Oh, question? Maybe? No? Okay. P of X of X, which is the number of casts, so throws of casts needed to obtain the first 6. And I'm realizing now why they have that first 6 that appears. Makes more sense. Okay, so our PMF, right, the probability mass function, looks at the probability of each outcome. So first, let's consider all our outcomes. And so our outcomes here, in theory, are 1, 2, 3, 4, technically all the way up to infinity, right? Not really in practice, because we know at some point, right, we're going to get a 6. If we cast the die enough times, we get a 6. But let's just think about our outcomes. Right? So what we find is we can set this up. We can have x as, oh, maybe I'll do it like this. X can be 1, 2. I'm not including 0 because in this case, I need to toss at least once to see a 6, right? And so we're ignoring 0 because I need to throw the die at least once. Okay, so maybe I'll make a note of that here. Excluding 0, since I need to cast the die at least once to see a 6. Right, if I cast it 0 times, then there's 0 probability of me seeing a 6, right? So you could look at that, but it's not going to contribute anything in this case. Oops, 3. So I've got 1, 2, 3, 4. Then I can find the probability of x, and maybe I'll use a capital P here. Probability of x. This keeps going, of course. We can map it out, right? So sometimes I find it useful if we just kind of visualize this thing. And so if I throw the die 1 time, right? And on that first throw, I saw 6. The probability of that happening is 1 in 6. Right? Now I've thrown the die 2 times. And I know because x equals 2, now I saw something other than a 6, which has a probability of 5 in 6, the first throw. So I threw it again. And on the second throw, I saw a 6 with a probability of 1 in 6. So then here, 2, 3, same idea. As long as the last one is a 6, right, then that's the probability of seeing a 6 on the third cast, right, on the third throw. So 5 and 6, 5 and 6, 1 and 6. Then the last one that we'll do, 1, 2, 3, 4. Same deal, 5 and 6, 5 and 6, 5 and 6, 1 and 6. And so on. Okay. So if we look at this pattern, okay, then what are we seeing here? So we want to try to make a connection between the, oh, nice, good. We want to try to make a connection between the x and the probability of x. If we can find some sort of pattern, which we can tell that there's got to be some pattern here, right? And so what we see is something of this nature. We see that this becomes 1 in 6 to the power of 1, right? Whereas this becomes 5 in 6 to the power of 1 times 1 in 6. And maybe I should write them with the same type of fraction, do a slanted one. To the power of 1, technically. And then 5 and 6 to the power of 2 times 1 and 6 to the power of 1. We know that it's because we're going until we roll the first 6, that 1 and 6 is always going to be to the power of 1, right? So that's nice. We can use that. So 5 and 6 to the power of 3 times 1 and 6, and so on. So to make a connection between, and maybe I'll use a kind of a lighter color here, to make a connection here between the x and something in here. So 5/6 and 1/6, we understand that those are the probabilities of rolling different values of the die, right? And so the area that I'm interested in is trying to connect this 3 to 4, right? And this 2 to 3, this 1 to 2, and technically 5 and 6 to the power of 0, right? And so I can show that here, because this is technically 5 and 6 to the power of 0, right? Anything to the power of 0 is 1. So now we can see this pattern that, okay, it looks like I end up at 5/6 to the power of x minus 1 times 1/6. And I kind of stopped doing the power of 1 here. So when x is x, that's what it's going to look like. So this becomes the PMF. So this is P of x, the PMF. That's hard to arrive at, right? It's not until you map out, okay, I'll just look at my first few to see if there's a pattern. Then I need to figure out what are those probabilities and can I summarize those probabilities, right? And then that's going to be our PMF. PDFs are for continuous functions, right? And so first thing we wanted to do was find the PMF. So we did that. Okay. So then we have found that P of x is 5 and 6 to the x minus 1 times 1 and 6. For x equal to 1, 2, 3. Those are the individual probabilities. So one property that we know is that, okay, if I look at all the probabilities, so the sum of all the probabilities, they have to sum to 1. Right? If I consider all these probabilities, all the possible outcomes, then they have to sum to 1. And so that's where the next part comes from. We want to show that this property that x from x equals 1 to infinity of P of x equals 1. Right? This has to be true for any PMF. And then the integral has to integrate to 1 for a continuous variable. Right? But for now, we're dealing with sums. And what's so funny is in the beginning, or usually I feel a little bit scared of integrals, but now I find myself just wanting to do integrals. I hate summations, these fancy sums. How am I supposed to recognize them? Well, they did have an example just like this in the textbook. I shouldn't say just like it, but very similar to this in the textbook in the beginning of the section. And so there, I was reminded that this is a geometric sequence. How am I supposed to remember that? Well, maybe put it in your memory bank. So the geometric sequence, we're gonna, if we have to do summations, I'm gonna tend to focus on the integrals because as you'll see, they're just gonna be a little bit easier, but the geometric sequence is one that we want to kind of have in our back pocket so it's available. Okay? And so if we look at this, notice that if I have the sum from x equals 1 to infinity of p of x, which is 5 over 6 to the x minus 1 to the 1 over, or times 1 over 6. This is a geometric sequence. Okay, so here, this is a geometric sequence. Okay. In general, a geometric sequence looks like this. And so it's the sum, and let me make sure I give it to you straight here. It's the sum of k equals 0, and you can use different variables here, but k equals 0 to infinity, let me clean that up, of a times r to the k. As a rule, this is a over 1 minus r, as long as the absolute value of r is less than 1, right? We can't deal with r's that are greater than 1, right, on the absolute value scale. So, all right, how can I make this connection? So mapping this geometric sequence, it does look like I have something like this, right? And so it's helpful to recognize this. In fact, if you're able to turn something into a geometric sequence, that's going to be really helpful, because then you know what the sum becomes. Right, so notice how this actually does the summation for you, and it turns into a over 1 minus r, which is really easy to deal with. So what we have, if we focus on what we do have here, I'm going to copy and paste it down here. Trying to connect things here. Right? I need an A and I need an R and I need a K. One thing is that K goes from 0 to infinity, but we can make adjustments there, right? And so, for example, if K is x minus 1, then when x is 1, K is 0. So that's really useful. So here we see that, okay, K is x minus 1. So when x equals 1, k equals 0. Okay, so that's good. So that takes care of this portion. And of course, going to infinity is fine either way. Infinity is infinity, so that's fine. And so we've dealt with this k. That's probably the hardest part. And then, so the r in this case is going to be, let me see if I can find a different color here. R is 5 over 6. Now, 1 over 6, that's our a, right? Because we're allowing for some constant. And of course, if a is 1, then you just have 1 over 1 minus r. That's even easier, right? If you don't have this here. But a is going to be 1 over 6. Okay. So, okay. Good. So I'm okay with the summation as is because I have x minus 1. Right, and so it's starting at basically a power of 0, and that's the most important part, right? As long as you're starting at a power of 0 and then letting it run to infinity, then that's the goal, right? And so here, this becomes a over 1 minus r, which if we plug in our values is 1 over 6 over 1 minus 5 over 6. One thing that I didn't check is that the absolute value of 5 over 6 is less than 1. That's good. So it's going to work, but I should include it, I guess. 1 minus 5 over 6 is 1 over 6. 1 over 6 over 1 over 6 is 1. We did it. But we did have to leverage that geometric sequence. Okay. Now, what's the next question? Okay, this one's really, really, really hard, right? Doing the same thing, but not for all values of x, only odd values of x. Uh-oh. Okay, how do we do it? I'd say it's probably the hardest one. C, how am I doing for time here? Because there were some later ones that, okay, this one is the hardest one. So we want to do this one, but then maybe I'll skip. Okay, it's okay. So I want to find the probability that x equals 1, 3, 5, 7. So this is odd values of x. No, if you say, if you do this mapping, that's okay. It would be useful if you referenced and said, because it's a geometric sequence, but you don't have to. You can just go to here. That's fine. Okay, so for the next one, what we want to do, these are odd values of x. Right? So we want to find the probability. So instead of summing over all the probabilities to end up at 1, now we want to look at, okay, what's the probability of only odd values of x? Okay. So what that's going to look like is we have, let's see here. Odd values of x. Let me map back to here. Okay. The sum x equals 1 to infinity. Okay. But for odd values of x, I could use a different variable here. And so, but I'm going to keep it the same, but just try to keep them straight. Is the same as saying 2x minus 1 for x equal to 1, 2, 3, 4, right? And so if odd values starting at 1, if I plug in x equals 1 here, 2x minus 1, 2 times 1 minus 1 is 1, good. If I plug in x is 2 here, I get 2 times 2 is 4, minus 1 puts me at 3. So far, so good, right? This is the pattern that I want. And so plug in 3, 2 times 3, 6 minus 1 is 5. Okay, good. Let's do the 4, and then we can assume that it behaves correctly all the way through. And in general, if you want odd values, you're going to use 2x minus 1. And then 2. Can't remember what you do for, should be easy, but odd values is 2x minus 1. I'm just trying to think of even numbers should just be 2x, but then 2 times 1 is, no, it works. 2, 4, 6, 8 works. All right. Never doubt yourself. 2x minus 1. Okay, so, and then let's do the fourth one. 2 times 4 is 8, minus 1 is 7. Okay, so it checks out. So the pattern that we want is actually 2x minus 1. We're going to let x run from 0 to infinity. So these are these x's in the summation. Okay, but what we're going to do is we're basically going to let k be 2x minus 1. Okay, and so let me just bring this over here. Okay. We can basically let, and I shouldn't let k, I'm using up all my letters. What's n? Anyways, maybe I won't call it anything. I'll just show you what I mean. So it's going to be 5 over 6. Oops. Clean that up. To the power of 2x minus 1 minus 1, right? Because you have, if you want the odd number, oh, sorry. Odd numbers, 2x minus 1. If x is, oh, if x is 1, 2x minus 1 is what? Well, 2x minus 1 is 2 times 1 minus 1 is 1, but the power that we want is actually 0. So now we're back to that 2x minus 1 minus 1 situation, right? And so it maps back to here. So 2x minus 1 minus 1 is what our power on 5 over 6 is going to be. That's all right. We can deal with that. In fact, it makes it easier. So we want 2x, and maybe what I'll do is I'll do it in light blue again. 2x minus 1, then minus 1. So that's from here. Times the 1 over 6. That's the same as before. So now subtracting this minus 1 is the same as it's starting from 0. Okay, and so by the same logic that we just used, right, k minus 1. But what I'm going to do is I'm going to rework this a little bit. So I get the sum from x equals 1 to infinity, oops, to infinity of 5 over 6 to the 2x minus 2 times 1 over 6. So then what I can do is I can pull out this common 2, and that's what makes it a little bit easier. Because now I'm just reworking it to look like another geometric sequence. Right now it's a little bit off, right? Because x is starting at 1 and I have a power of 2x minus 2. So now I'm going to rework it and I have the sum from x equals 1 to infinity of 5 over 6 to the power of 2 times x minus 1 times 1 over 6. Okay. So to make it look like what we were just dealing with, right, with a k of x minus 1, then I can bring this 2, right, exponent laws, let me bring this 2 onto the 5 as well as onto the 6. And so what I get is I get the sum from x equals 1 to infinity of 5 to the power of 2 over 6 to the power of 2 to the power of x minus 1 times 1 minus 6. So then again, just like before, k is x minus 1, but when x is 1, k is 0. And then it goes to infinity, that's fine. And so now we have, just doing the same mapping here, I guess I use different letters or colors. I can still finish it if I do orange. I'll have the same setup. R is 5 squared over 6 squared. That's 25 over 36. And then I think I had A is 1 over 6 still. Okay. So as long as K is running from 0 to infinity, then I can apply this the geometric sequence. And so I have A over 1 minus R. I'm going to check that R, the absolute value of R is less than 1, but 25 over 36 sounds like it's less than 1 to me. It is. It's 0.6944444. So we're good to go. I'll check it here just in case. Absolute value of R is less than 1. It checks out. So then what I have is I have A over 1 minus R. In this case, we get 1 over 6 over 1 minus 25 over 36. And I'm just going to do it here on my calculator, 1 over 6. Otherwise, we have to deal with all kinds of common denominators and flip and multiply, and we'll save that fun for later. So I end up at 6 over 11. Whew. Tricky. But the key is to morph this thing into something that we can work with, right? And so as soon as you see a summation that you don't really feel like dealing with, see if it can be transformed into a geometric sequence, right? That's going to be your first plan of attack here. Okay. Part D, we want to find the CDF, which is capital F. Usually we use a capital F for the CDF, which is the probability that X is less than or equal to some X. So what that's going to look like is another geometric sequence, but now we have this finite sequence. And so I'll show you. Let's see here. F of X, it's going to be really confusing to talk about X's in terms of these X's for a little bit. And so maybe what I'll do is I'll change this to a Y. Okay. F of Y is the probability that X is less than or including or up to some Y. Okay. So these are for a function that is easier to read. You could use X, but you'd have to keep them all separate. Okay. So what is this? So the CDF is the probability of being up to and including some point Y. So we're really just summing up to Y. So this is going to be the sum from X equals 1 to Y of the original PDF, which is 5 over 6 to the X minus 1 times 1 over 6. Okay. And so here, what happens when we have this is we've got this finite geometric sequence. So X from 0 to, let's say, K. I guess I could have used the K here. Is going to be of that geometric sequence. I didn't write it down, so that's why I'm trying to backtrack here. Oh. How about that? What if I told you, what if I tell you this? I have an A1 here. Why didn't I write it down? I'll never think of this stuff on the spot. Anyways, there's an A1, but I'm gonna ignore it for now, and it just becomes A times 1 minus R to the K over 1 minus R. That's the important part. Should have written down the proper sequence here. Maybe before I post the notes, I'll go back, I'll find it. I don't remember it off the top of my head. And you don't have to either, right? Once you use these enough, and I haven't done enough practice of these in a long time. So, but once you've done enough of these, you're gonna start to recognize sequences that you use a lot, right? It's just like learning a language, right? In the beginning, when you hear a new language, you don't hear distinct words, right? It's just all one thing, right? And then when you practice, you start to hear those distinct words. And so here you're going to start to see these sequences, right? And they're going to kind of come at you, or you'll see something that you think, oh, I could make that into a sequence that I know how to deal with. We are going to focus on continuous variables most of the time, but we need to be able to deal with discrete variables. So anyway, so this becomes, from here, right, it becomes 1 over 6 times, and here I'll 1 minus 5 over 6, because here I have R is 5 over 6, K equals Y, and A equals 1 over 6. 1 minus 5 over 6 to the power of Y over 1 minus 5 over 6. One minus 5 over 6 is 1 over 6. 1 over 6 over 1 over 6 is going to cancel out. And so I'm just left with 1 minus 5 over 6 to the Y. Right. And so the CDF up to some value Y. And so now I could morph this back to some f of x. But that's just replacing the Y with an X, 1 minus 5 over 6 to the X. Yeah. Good. (1.6.9). What we did, we wanted to find, let X have PMF. P of X is 1 over 3. For X equal to -1, 0, and 1. Then we're going to find the PMF of Y equals X squared. Find the PMF of Y equals X squared. I'd say the easiest way to deal with this one, because I have these unique values of X, right? And I have the probabilities. If X is -1, 0, 1, then the probability of X is 1 and 3, 1 and 3, 1 and 3. It's a uniform distribution here. 1 and 3, 1 and 3, 1 and 3. So now I want to look at y equals x squared. So y equals x squared, and I want to find the probability here associated, but first I have to find the different values of y. So if y is x squared, -1 squared is 1, 0 squared is 0, and 1 squared is 1. Notice that we only have 2 values of y now, right? And so the probabilities stay the same here, 1 over 3, 1 over 3, 1 over 3. And so, but P of y is going to be 1 over 3 when y is 0, and 2 over 3 for y equals 1. 0 otherwise, but I'm ignoring that case. Maybe I shouldn't. 0 otherwise. So that one's kind of a quick win, but I fear that what might have happened is you probably overthought it a little bit because you've been working through these hard problems that you couldn't slow down and smell the roses for kind of an easier one. And there's another one like that in here, but the other ones are really hard, so I don't blame you. 1.7.11. I said no graphs needed, and that applies to all of these. If you find that how you answer the question is easier with a graph, then of course you can include it, but I never want you to feel like you have to hand draw a graph. That's crazy talk. And so you don't have to include graphs. Don't worry about that. That was kind of a broad strokes. No graphs needed in work. I'll do it because, of course, makes it easier, right? So I'll show you, but it's only easy if you're working on like a tablet, so don't worry about it. Okay, so 1.7.11, I think, is the next one we want to do. Let me find it. For each of the following CDFs, find the PDF or the PMF in Part D, the first quartile and the 0.6 quartile. Also sketch the graphs of f of x and f of x. May use R to obtain the graphs. You don't have to do that. No graphs needed. And for Part A, they've included that code to get you started. And that's going to be useful for the follow-up question too, especially if you don't know, if you don't feel comfortable graphing in Desmos yet. But all of these can be graphed in Desmos as well, which is what I'll be using. Because when I run R and I have a Zoom meeting, it really slows everything down. But okay, let's see here. So A, we're given that f of x is 1 over 2 plus 1 over pi inverse tan of x. And x is just the set of real numbers, -infinity to infinity. Okay, so first thing we have to do is find the PDF. Find the PDF. So what we need to remember is f of x is the derivative of the CDF. Okay, so the derivative of this with respect to x right? We've got a constant plus the inverse tan. Now, of course, I posted those calculus kind of reference sheets at the top of our Moodle page, and it's for this reason. I don't expect you to remember that it's 1/1 plus x squared, the derivative of inverse tan, but I do expect you to be able to read the reference sheet and then plug it in. Okay. So, okay. The derivative of this thing, well, we get 0 plus 1/pi times the derivative. X is really only showing up here in the inverse tan. So the derivative of the inverse tan is 1/1 plus x squared. See calculus reference sheets posted on Moodle. I'm going to try to find a cheat sheet of all the common sequences that you might find useful. And so because I noticed it wasn't, I thought it was in that reference sheet. I just kind of flipped through it, but it doesn't look like it's there. So I'll try to find something like that. So you have, a reference sheet. Okay. But if I go through and I deal with this, then 0 goes away, 1/1, 1/pi, and I'm just left with 1/pi times 1 plus x squared. Okay, that's the PDF. That's the probability of an individual value of x. Okay. Now, we want to find the first quartile. That means we have to remember what the first quartile is, in fact, what a percentile is. And so recall the pth percentile, is the value of x that has p% of the curve below it. Okay. So is the value of x with p% below it. That's the same as the CDF, right? And so what that's going to look like, and I'll keep it, I guess, the probability that x is less than or equal to x, which is our CDF. Okay. So the pth percentile is really just the input of x that makes f of x be the percentile that we want. That's hard, right? And so the first quartile is, and I'll bump this down here, first quartile is the 25th percentile. Which means the area to the left of some point, x, is 0.25. Which means the area to the left of x is 0.25. So what we're actually trying to find is where the value of x, where f of x equals 0.25. Crazy. Okay, so we were given f of x. So then I could solve for the value of x that makes that happen. So for the first quartile, I have f of x, I'll bump it because I've got a fresh page here. F of x is 1/2 plus 1/pi inverse tan of x. And I'm going to force it to be 0.25 and solve for x. Okay. 0.25, if I'm solving for x, I'm just going to massage this a little bit. I'm going to move this 1/2 over here. So then that puts me in negative 0.25. And so I have 1/pi tan inverse of x is negative 0.25. Okay. I'm going to multiply this pi over here, right? Negative 0.25 pi. So then I have tan inverse of x is negative 0.25 times pi. I've got the tan inverse, so I can just take the tan of both sides. And so then I have x is the tan of negative 0.25 pi, sorry. Which, if we do it on your calculator, make sure you're in radian mode. Right. Always calculate trig functions in radian mode, unless it has a little degree symbol, right? But as soon as you see a pi, you know you have to be in radians. And so make sure you're in radian mode. On mine and most calculators that I've ever seen, they have a little reminder up here. There's a DRG. You're not the only one, so don't worry. Right, and it has happened to me many times. So you want to be in radian mode, and so figure out how to change it into radian mode, and then what we have, then you can just plug it in. So now we have negative 0.25 times pi. Use the pi button. You should have a pi button on there somewhere. Use the pi button. And if I take the tan of that, x equals -1. Right, so make sure that that's what you end up at. Okay. So same thing goes for the 60th percentile. What do? All we have to do is we have to change this to 0.6, right? And so, and then we can go through and we can solve it. So let's see here. If we graph it, if I graph the CDF, 1/2 plus 1/pi times the inverse tan, and there should be an inverse tan function here of x, I get this graph. Okay. So what I'm trying to solve is where y equals 0.25. That's going to be at -1. We just found that, right? We found it the hard way, but you can use the graph too. They want you to try both, but y equals 0.6. From the graph, we see that we're at 0.325 roughly. So that's an approximation, but it's close enough for me. So I'm going to screenshot this. And so just kind of try to keep it here. We see the 60th percentile will be at x approximately 0.325, because I went through and I did the calculation, and so it does round to 3 decimal places, and so that's what it's done. Okay, so what I want to do is I promise I'll post, I'll add the solutions to the remaining parts just so you have them. Okay, But then I want to move on to the next question because I am so out of time, but I feel like we can do it. Okay. And actually, the one that I really want to do is the last one. I know 1.7.21 was really hard, but I'll post the solutions, how about, so you can reference them. Okay, and I want to skip to 1.7.22. Okay. So 1.7.22, and don't worry, I will post the rest of the solutions. They'll be squeezed in here. Okay, 1.7.22. We're gonna let X have PDF be f of X is X squared over 9. And X is between 0 and 3. 0 elsewhere, but that's understood. So then find the PDF. Find the PDF of y equals x to the power of 3. Okay. And so this is from transformations, right? And so to find a transformation, because we can no longer list all the possible outcomes and look at all the different values, right? That's impossible at this point. 0 to 3, there's an infinite number of values between 0 and 3. And so now what we have to do is we have to apply an actual transformation. So we had a bunch of steps that we were going to follow, right? And so step 1 is find the support of y. Now that's basically finding, what are the possible outcomes of y? Well, if x to the power of 3, so x is between 0 and 3, then y, which is between 0 and 27, right? 3 to the 3 is 27. Phew. So then what we find is that y is between 0 and 27. Maybe I'll follow this up with y equals x to the 3. So I shouldn't say just, but you look at x, the range of x, and if you have to go, if you have another class, that is totally fine. I'll keep this in the recording, but I am going to keep going here so that you have this solution, because it's part of that video that I got you to watch. So we haven't talked about it in person. So that's why I want to have it here. So the first thing we're going to do is find the support of y. Okay, so we've done that. So the second thing we have to do is we have to solve for the inverse of the transformation. Solve for the inverse of the transformation. So the blue parts are really the only parts that you need to show, but I find that it's helpful if we have some steps to follow. So then if y equals x to the 3, then x is going to be the third root of y. Okay. Good. Or y to the 1 over 3 if you prefer. Oops. Or x is y to the 1 over 3. Okay. Next thing you want to do is you want to find the Jacobian. So the Jacobian sounds fancy, but find the Jacobian, which is really just dx dy. So in our case, it's going to be the derivative dx dy is going to be the derivative of y to the 1 over 3. So y to the 1 over 3 is 1 over 3. This is with respect to y, right? And so I'm taking the derivative of x with respect to y, right? And so the derivative of x with respect to y, well, that's going to be 1 over 3 times y to the 1 over 3 minus 1 is what, negative 2 over 3, I want to say. Okay. So then my fourth step is to put this all together into the transformed PDF. So Fy of y is Fx of g inverse of y times the Jacobian, or if you prefer dx dy. But it gets confusing because it might look like you have to take the derivative, and that's not what you're doing here. And so this here is basically write out the original PDF with the y equals x to the 3 replacing the x, right? Or with x as y to the 1 over 3. Okay. And so, and maybe I just do it because I'm short on time here. Fy of y is going to be, in this case, x squared over 9. That's my f of x. But now I'm saying that, okay, x is actually going to be replaced with the third root of y, or y to the 1 over 3. So this becomes y to the 1 over 3 squared over, shoot, I think it was 9. Yeah, x squared over 9. Over 9 times the derivative, which we just found, 1 over 3 times y to the negative 2 times y to the negative 2 over 3. I can simplify this, right? Especially if I move this y downstairs and I bring this 2 inside, I get y to the 2 over 3 over 9 times, and maybe I should collapse this 1 over 3, but times 1 over 3 y to the 2 over 3. But this is going to go away. So then I just have 1 over 9 times 3. 9 times 3 is 1 over 27. So it's a uniform function. Okay, I know I went over time, but that's the one that I really wanted to get to. And as promised, I will fill in the solutions before I post them, and you can have a look back. If you have any questions, let me know. Otherwise, I will see you on Thursday. Stop this here.